Today, our goal is to understand how we use standard candles and a distance ladder to find how far away things are from us here on Earth. Go ahead and write the question of the day down. How do we measure the distance to very distant objects up in space? What we do is we use what's known as a distance ladder. And the distance ladder is a metaphor for how astronomers use different methods to find distances to different objects. No one method is going to work for all distances. If you're really close, you can use certain methods. If you're an object that's a little bit farther away, you have to use different methods. So by using all of those methods and overlapping them, they're able to figure out how far away most things in the universe are. The key to all of this are standard candles. Standard means it's the same all the time. Candle just means that it is giving off light. So a standard candle is an object that gives off the same amount of light no matter where we see it in the universe. Each and every one of them is the same brightness as every other version of that object.
Imagine that you're walking around Greenwich Park at night, and you see a light. If the light moves away from you, you'll see it appear to get dimmer, and if it moves towards you, it will appear to get brighter. If you know exactly how luminous the light is, say it's a 40-watt bulb, you can use how bright it looks to you to work out its distance from you. And you can do the same for any other 40-watt bulbs. But other types of light could either be dim and up close, or bright and far away. Only objects of known luminosity, called standard candles, can be used to measure distances. There are lots of different things in the universe that we use as standard candles.
This is an infographic showing that depending on what you want to find the distance to, like how far away it is, you're going to be using different methods. So within our solar system, we're going to use this method. If we want to see things within our Milky Way, we can use this method. If we want to see distant galaxy clusters, we can use these methods. So different distances of objects are going to require different methods. All of the objects that were on that picture are on this slide. I'm going to go through them really quick, and then we are going to go through each one individually. The first method is to use radar. The second one is a method called parallax. And then we get to main sequence fitting, and then we get to Cepheid variable stars. You might notice that some of these are familiar. I know that I've mentioned parallax. Hopefully you know what a main sequence star is. I know I've mentioned Cepheid variable stars as well. And then we get to the Tully-Fisher relationship, which we haven't talked about, and supernova type 1a, which we have talked about. Finally, we get to Hubble's law, and we are going to spend all of next week, all 5 days, learning about Hubble's law. But we are going to mention it today. That Virgo cluster that we looked at yesterday, the one that's about 50 million light years away, if you use different methods, you are going to get roughly the same, but a little bit different distances. So a lot of objects up in space, astronomers will use different methods to calculate the distance to the same object if they can. And then they can use kind of an average of all of those different methods. So this Virgo cluster, about 50 million light years away, you can get, using Cepheid variables, roughly 15 megaparsecs. If you use supernova type 1a, it's all the way up to 19.5 megaparsecs. But there are a number of different methods of finding distances, and they all are going to give back a little bit different answers. But I want to point out the fact that they are all relatively bunched together means that they are doing the job correctly. If all of a sudden you got one of these that was like 500, well, all of a sudden something is majorly wrong. But because we are talking about distances that are so huge, as long as they are pretty close together, and in this case they are, then you can be confident that your methods are working. Let's go through each of these. The first one is... Scared the crap out of me. Oh my god. Well, that woke me up. Alright, so the first method is known as radar ranging. Very simply put, we shoot a radar beam at an object, it bounces off that object, and we time how long it takes to get back to us. Because we know the speed of light very accurately, we can measure how long it takes to get to that object, and then come back. Objects inside of our own solar system are close enough that we can send out radio signals to them, wait for them to bounce off, and get those radio signals. However, objects outside of our solar system are a little bit too far away for that to happen. So we can measure very accurately, in some cases down to like the centimeter, in the case of the moon, how far away things in our solar system are by shooting out radio waves at them.
The way we tell the distance to objects within our own solar system is something called radar ranging. What this basically is you're here on the Earth. Here's my little satellite dish. And you have an object, let's say it's the moon, which is over here. The speed of light is constant in a vacuum. So if I launch, let's say, a radar beam or other things from the electromagnetic spectrum, it's going to take a certain amount of time for it to reach there, and then a certain amount of time for the echo to come back and reach our sensor again. Now, the speed of light being constant, we can then figure out exactly how far away that object is. So that works for objects that are within the solar system. Asteroids, Jupiter, the moon, all of those types of objects. It doesn't really work for the sun, because the sun is emitting this type of radiation all the time, and so we're never able to pick up these tiny little things that should be bouncing back. The sun just washes it all out.
The next method is parallax, and I know that I've mentioned parallax because I remember doing this, but that's where you hold your thumb up and you switch which eyeball you're looking at your thumb with, and because your eyes are looking at your thumb at slightly different angles, you're going to see your thumb seem to bounce back and forth. Well, if we take a picture of a close-by star on one side of our orbit, and then we wait 6 months, and we take a picture of that same star from the other side of our orbit, whatever's in the background of that star will seem to switch. So right now, hold your thumb up against something in the room that you're in, and look at your thumb with one eye closed, and then switch which eye is looking at your thumb. And your thumb will seem to move against the background. We do the same thing with close-by stars on either side of our orbit, and they will seem to move against the background. And because we know how big our orbit is, 2 astronomical units, we can then calculate how far away that object is using trigonometry. This works extraordinarily well for close-by stars, because they're close enough to seem to bounce back and forth using parallax. So we have very accurate distances for hundreds and hundreds and hundreds of stars. Once you get more than a couple hundred light years away, though, then our orbit is not big enough for those stars to seem to move using parallax. We're going to have to look at something else. But for those hundreds and hundreds of stars, we know exactly how far away they are.
Have you ever traveled down a road in a car and looked at the mountains or hills in the distance? If you have, you've probably noticed that while nearby trees quickly fly past the window, the mountains move much slower, and in the far distance, the moon and the stars don't seem to move at all. As you move, objects closer to you, such as the trees, seems to shift position relative to more distant objects, like the mountains. This effect is called parallax. The size of this shift depends on the distance you travel along the road and how far away the trees are. The closer they are to the road, the bigger the shift. The same thing happens as the Earth moves around the Sun. Over the course of a year, some stars appear to move a very small amount relative to other stars. Like the trees along the side of the road, these stars are just closer than those that don't seem to move. Actually, all stars are moving through space, but much more slowly than parallax, so we don't notice. Now, if we measure how much a star moves when the Earth does one complete trip around the Sun, we can use this to work out this angle, called the parallax angle. If we observe a star when the Earth is at one spot in its orbit, and then wait 6 months for the Earth to move around the Sun to the opposite point along its orbit and observe the star again, we can measure the parallax angle. Since we already know the distance from the Earth to the Sun, we can now use this parallax angle and some trigonometry to work out exactly how far away the star is. This is really useful because it allows us to calculate the distance to nearby stars very accurately. This can then be used to check the distance measured by different methods to even more distant objects out in space.
So what do we do with those hundreds and hundreds of stars that we know exactly how far away they are? We put them on an HR diagram. We know their temperature because we can see their spectrum and look at blackbody radiation. We know exactly how bright they are in real life because we know how far away they are. And so we can plot a pretty accurate HR diagram using hundreds and hundreds of stars. And now, as soon as we find a new star that maybe is too far away for parallax to work, As soon as we measure its temperature, well, we plot it on an HR diagram, and that will tell us its luminosity. We compare that to how bright we actually see it, and boom, all of a sudden we know its distance. So let's say you find a brand new star, and this brand new star is, I don't know, 15,000 degrees. It's really hot. You don't know how far away it is, though. All you know about it is its temperature because you can see its spectrum. So you plot it on this HR diagram, which we have very accurately drawn with these close by stars, and at 15,000 degrees, that's going to put the star right about here. Well, because the HR diagram then will also tell us the luminosity, we know exactly how bright it should be. We compare that to how bright we see it, and we have the distance to that star. This is known as main sequence fitting. All you do is take a new star, fit it onto the main sequence of an HR diagram that you've already created, and you can figure out its luminosity and therefore its distance. If you are curious on how to go from its absolute magnitude to its apparent magnitude and find the distance, here is the equation. You'll never have to do that in this class, but as long as you have a calculator and you know how bright it's supposed to be, you can measure how bright it really is. It's a matter of seconds before you find out its distance. Cepheid variable stars. These are those stars that change in their luminosity over time. So they get bright and then dim, and then bright and then dim. And how fast they do that tells us how bright they really are. Henrietta Swan-Leavitt figured out that if they do that really, really fast, they're actually pretty dim. If they do that very slowly, then they are very, very bright. We can calculate exactly how bright those stars are. And when we see them in a distant galaxy, we can calculate how bright, how much light is coming out of that star. You compare it to how bright we see it, and all of a sudden you have the distance to that distant star. The cool thing is we can see these in other galaxies. And so if we can calculate how far away that star is, we know how far away that entire galaxy is.
Astronomers can rely on a standard candle, which is a celestial object whose luminosity is well known and used to find the distance to a faraway object, like a galaxy. The best standard candle are called Cepheid variables, which are variable stars, stars whose brightness varies as seen from Earth. By comparing the apparent brightness of a Cepheid variable with its luminosity, meaning its intrinsic brightness, astronomers can find the distance to the galaxy that contains them.
The Tully-Fisher relation, named after the two guys who came up with this. So galaxies rotate. They are going to rotate around a supermassive black hole. The bigger the galaxy, the faster it spins. If it's a small galaxy, there's not a whole lot of gravity holding it together, and if it spins too fast, it will fly apart. The more gravity you have, the faster you are going to be spinning. So far, so good. We can actually use hydrogen lines from one edge of the galaxy that will be blue shifted as it comes towards our telescope, which means the hydrogen lines coming from the other edge of that galaxy are going to be red shifted. We can use the Doppler effect to calculate how fast it is spinning. Turns out there's a very strict relationship between how fast it spins and how big that galaxy is. There's also a relationship between how big that galaxy is, how much stuff is in it, and how bright they are. Because if there's more stars, they're going to shine brighter. We then plot all of that data, and we can draw a best fit line through it. And it turns out that if you are spinning faster because you're a bigger galaxy, you're going to shine brighter. We now can see a distant galaxy that is way far away, calculate how fast it is spinning because we look at the red shift of those hydrogen lines, and if we know how fast it's spinning, all of a sudden we know its brightness. We then calculate how bright we see it compared to how bright it should be. That will tell us its distance. And we can do this for galaxies millions of light years away, which I think is pretty cool.
Observationally, the luminosity of spiral galaxies is correlated with their rotation speed of their gas disks. There's a physical basis for this distance indicator, because the rotation of the gas disk is an indicator of mass, and if the mass-to-light ratio of a spiral galaxy is relatively constant, then it's also an indicator of luminosity.
And now we get to these white dwarf supernovas that we've also already talked about. And remember, these are those supernovas that happen when a white dwarf star is stealing material from its red giant neighbor. And when it gets to the Chandrasekhar limit, 1.4 solar masses, boom, the whole core fuses at once. You have a type 1a supernova. We know exactly how bright that is because it is the same explosion every time it happens. It's the same brightness. No matter which white dwarf it is exploding, it's always the exact same brightness. So we compare how bright it's supposed to be versus how bright we see it, and that can tell us how far away that object is.
To find the distance to galaxies. So one way in which we could do that is by studying type 1a supernova explosions. They last about 30 days. It's when a white dwarf star exceeds its Chandrasekhar limit, exceeds 1.4 times the mass of the sun. When it does, the star simply explodes, and when it does, it has a maximum brightness of -19. That's the absolute brightness. Now notice the explosion lasts for about 30 days. It takes several days to reach up to its maximum value. If we measure it correctly and we watch it correctly, we can find out when that happens. We then try to measure the apparent brightness, and we compare the two things. So let's say we have an apparent brightness of about +10. So that means we were looking at it with a telescope, we kept measuring it and measuring it. We reached its maximum value, we tried to measure the brightness of that galaxy. We then know, of course, that the absolute brightness, the real brightness, is -19. And then, of course, we simply take the difference. So what that means is that if the actual explosion happened at a distance of 10 parsec, it would have a brightness of -19. But instead, when we measure it, since it's so far away, it only had a brightness of +10. That's a difference of, let's see here,
and we get 3.99 times 10 to the 11th.
Big number. All right, so that would be the difference in intensity, the difference in luminosity to where it's actually occurring to where what it would be if it was only 10 parsecs away. So therefore, to find out where it actually occurred, the distance, we take the So that means that D equals about 6.31 megaparsecs, which is about 20 million light years.
These can be seen billions of light years away. So if we see a galaxy that has one of these type 1a supernova in it, we can calculate how far away that galaxy is. And then if that galaxy is in a group or a cluster of galaxies, we can determine about how far away that entire cluster of galaxies is. Now this obviously isn't going to work to figure out how far away the moon is. This also wouldn't work to figure out how far away the closest star is. But it does work for things across the universe. Just like shooting a radio signal towards a distant galaxy millions of light years away is not going to help us at all. You have to use different methods in order to find the distances to different objects. And now Hubble's constant. We're going to spend all of next week looking at this. Edwin Hubble, that guy who classified galaxies, had a cool space telescope named after him, he was looking at distant galaxies. Distant galaxies that had Cepheid variable stars in them, so he could figure out how far away they were. He was before the Tully-Fisher relation, so he wasn't able to use that, but he was able to use Cepheid variable stars and figure out how far away very distant galaxies were. He noticed something strange. He noticed that as you got farther away from the Milky Way, galaxies started traveling away from us. And when you got a little bit farther, they're traveling away from us a little bit faster. Galaxies a little bit farther than that are traveling away from us just a little bit faster. Now this doesn't hold for galaxies close to us. So those in our local group are all held together by gravity. So this isn't happening in our local group. Not even really in the Virgo supercluster. But outside of that, if you look at galaxies, they're moving away. And the farther you move away from our Milky Way, the faster they seem to be going. So now, what we do is similar to how we use the HR diagram. If we find a new galaxy, all we need to do is measure its redshift. And if we can measure its redshift, we know how fast it's moving away from us. If we know how fast it's moving away from us, we put it on this little diagram, which represents Hubble's law. All of a sudden, we're going to be able to figure out how far away that object is.
Looking at galaxies containing standard candles, astronomers found that the light from all distant galaxies was redshifted. The more distant the galaxy, the greater the redshift. We now understand this is because our universe is expanding. From our viewpoint, all distant galaxies seem to be moving away from us because the space between us and them is stretching out. More distant galaxies appear to recede faster because there is more space between us to expand. Light waves traveling to us from distant galaxies are redshifted, not because they're moving away from us, but because they've been stretched out as they traveled to us through our expanding universe. We know how far away things are in the distant universe by measuring how redshifted their light is.
I just gave you guys the cliff notes for Monday's entire lesson. So I'm going to go into this a little bit more in depth. I'm going to explain it a little bit more. But basically, you look at a galaxy's redshift, and that will be able to tell you how far away that galaxy is. I've mentioned this a few times. If we did not have the method of parallax, well, finding out that Cepheid variable stars have that period luminosity relationship wouldn't help us any, because we wouldn't know how far away the closest Cepheid variable stars are. We have to be able to get parallax to figure out how far away those Cepheid variable stars are, so that we can then calibrate all Cepheid variable stars. And if we didn't have these, it doesn't matter if we knew how bright supernova type 1a are, because we would just be guessing as how far away they are. But because we have Cepheid variable stars and supernova in some distant galaxies, we can basically determine the distance to that galaxy using a Cepheid variable star, and then we can calibrate the method of using supernova in order to calculate distances. Which is why we refer to this as a ladder. Because if you don't have the bottom rungs of the ladder, parallax, Cepheid variable stars, the top rungs, the farthest away objects, like supernova and looking at redshifted galaxies, those methods are not going to work.
What's most incredible to me is how all these measurements build on each other. It's only by knowing the scale of our solar system, the distance between the Earth and the Sun, that we're able to measure the distances to nearby stars using parallax. If we can learn how far it is to some nearby standard candles using parallax, we can then use comparison between standard candles to measure the distances to farther stars and galaxies. Finally, by studying the motions of galaxies with standard candles, we learn we can use redshift to measure distances throughout our expanding universe.
Go ahead and sketch this in your science journal. Use an entire page, and what I want you to do is write down the method. I also want you guys to write down how far away that method works. So radar ranging, for instance, works within our solar system. Parallax works for nearby stars. Cepheid variables can work in nearby galaxies. So write down the method, draw a sketch, and tell me what type of distances that method works with. Now that we've gone through each one of these methods, you've done it in your science journal, let's have a recap.
Considering how massive our universe is, we know the distances to cosmic objects surprisingly well. Like, we know the moon's distance from Earth so precisely, we can tell it increases about 3.8 centimeters each year. And we can also measure distances that are so enormous, they sound like made-up numbers. To do that, astronomers use what's called the cosmic distance ladder. Each rung of this metaphorical ladder is a different way of measuring astronomical distances. And from the bottom to the top, it goes all the way from the moon to the most remote galaxies we've ever found. People have been measuring distances within the solar system for millennia. For example, the ancient Greek astronomer Hipparchus used what's now high school trigonometry to estimate the distance to the moon during a solar eclipse. He was able to do that because eclipses look different from different places on Earth, for the same reason that if you close one eye and hold out your thumb, it'll cover one spot on the wall, but if you switch eyes, it will cover a different spot. This effect is called parallax, and during a solar eclipse, the moon acts as your thumb, while different cities are like different spots on the wall. So by measuring what fraction of the sun was visible in one city when it was a total eclipse in another, Hipparchus was able to do a little math and calculate the distance from the Earth to the moon. And he came pretty close to the right answer, too. We know that because today we can use light to get a much more direct measurement. We just bounce a laser beam off the moon and time how long it takes to return. We already know how fast light travels, so with these two pieces of information, we can solve for distance. This technique works incredibly well within the solar system, and it doesn't just tell us the distances to objects like the moon and nearby planets. It also shows us that many older measurements were extremely accurate, and that good old-fashioned trigonometry can be a solid way to calculate cosmic distances, which is good to know, especially when it comes to objects we can't bounce light off, like the sun, which is too bright, or objects outside the solar system, which are too far. In fact, trigonometry is the best way to measure distances to most nearby stars. For those, astronomers still use the same trick the Greeks pioneered: parallax. As Earth moves from one side of the sun to the other, nearby stars seem to move a tiny bit compared to more distant ones. Again, it's like when you hold your thumb up and close one eye. As your perspective shifts from one eye to the other, closer objects seem to move, while distant ones seem to stay in the same place. So, based on how much something seems to move, you can tell how far away it is. Parallax works great for stars within about 3,000 light years from Earth, or several quadrillion kilometers. But after that, the shifts get too small to measure. So for more distant objects, we need to climb up another rung on the ladder. Scientists first took that step in the early 1900s, when the astronomer Henrietta Swan Leavitt discovered a special type of star called a Cepheid variable. These stars are variable because their brightness fluctuates over time, and what makes them special is that the rate of those fluctuations is directly related to how bright they are on average. That means that no matter how dim they seem from Earth, you can figure out how bright they truly are based on how quickly they vary. And conveniently, brightness is tied to distance in a predictable way. It's like if you saw one candle right in front of you and another at the end of a hallway. The one closer to you would appear much brighter. As a result, Cepheid variable stars became the first known standard candles. A standard candle is any object whose absolute or intrinsic brightness is consistent, meaning you can use its apparent brightness from Earth to figure out its distance. In fact, just 15 years after Leavitt's discovery, Edwin Hubble used Cepheids to measure distances to objects well outside our galaxy, showing, for the first time, the Milky Way was not the entire universe. These days, we have lots of kinds of standard candles, which is helpful because Cepheids aren't the brightest, and you can't always find one where you need one. For instance, in some cases, astronomers can use supernovas as standard candles. These exploding stars are so bright, we can use them to calculate the distance of galaxies deep in the universe. And sometimes, even galaxies themselves can be standard candles. The faster a spiral galaxy rotates, the brighter it is. So we can use that fact to figure out the relative distances between galaxies. There are plenty of other standard candles too, but the cosmic distance ladder isn't one big candelabrum. For extremely distant objects, or ones that don't contain a standard candle, astronomers have to get really creative to measure their distances. They can make educated guesses by looking at how much the light has stretched out between the source and Earth, or how light bends around a massive object. In short, there's no one-size-fits-all solution, and the cosmic distance ladder is still getting new rungs. What's incredible is that even though astronomers are dealing with numbers that seem absolutely ludicrously large, they can be pretty confident in their measurements, because each step on the cosmic distance ladder overlaps at least a little with the one before it. So each rung of the ladder double-checks its neighbor. And that means we can map out distances to nearly anything from the moon to the edge of the universe. If you want to find out more about the discovery of the first standard candle and the brilliant astronomer behind it, you can learn all about it in our Great Minds episode on Henrietta Leavitt.
If you guys could go back and answer the question of the day, I'd appreciate it.